The integral from -1 to 1 of the product of two polynomials defines an inner product on the space of polynomials with real coefficients. But if you've never seen this before, you might be wondering, like, why is this an inner product? Why is this even a natural thing to consider? How did anyone come up with this? So in this video, I'm going to try to explain to you that, in fact, that inner product, the integral from -1 to 1 of the product of two polynomials, is actually a generalization of the usual dot product. And to see the connection between the two inner products, we can have a closer look at what is a Riemann integral. We can approximate the Riemann integral from -1 to 1 of the product of the two polynomials by a Riemann sum. So what I'm doing is breaking the interval from -1 to 1 into n subintervals, each one of length delta x, and then the Riemann sum will be an approximation of the Riemann integral. This Riemann sum, this is the left-hand side Riemann sum, and it will be the length of the intervals, delta x, times a sum of values of the function, in this case p times q, evaluated at the left-hand side of the subintervals. And that sum right there looks very much like the inner product of two vectors. In fact, we can reinterpret the dot product as if it was a sum of values of some functions. Let me show you. We could consider v as a function from the set 1, 2 up to n to the real numbers, such that v of k is the kth coordinate of the vector v. And if you think of v as a function, then we can reinterpret the dot product of v and w, the usual dot product, as a sum of product of values of the function v and the function w at the numbers 1 through n. And now that resembles the Riemann sum that we had before. So this is the discrete version of what we did before for a continuous function. So if we have functions that are discrete or take finitely many values, we can do a discrete version of the dot product. And if we have functions that are continuous and take infinitely many values, for example, between -1 and 1, then we can do a continuous version of the dot product by taking the integral from -1 to 1 of the product of the values of the functions. And as you can see, that is defined as a limit of Riemann sums as the length of the subintervals goes to 0, and that very much resembles a discrete version of the dot product. And this not only works for polynomials, it works for any continuous function in the interval from -1 to 1, where we can define the inner product in the same way, and it's a generalization of the usual inner product.